Alright, so hello guys. Today we are going to be discussing the editorial for weekly contest 493, and we're going to discuss all the problems in this contest. So yeah, let's go. Okay, let's begin with the first problem. It says that you're given an integer n. Return the total number of commas used when writing all the integers from 1 to n inclusive in standard number formatting. So in standard formatting, a comma is inserted after 3 digits from the right. Numbers with fewer than 4 digits contain no commas. Okay. So basically, we have been given this upper bound n, and from 1 to n, we need to calculate how many commas do we have in total, right? So let's say 1000 has only one comma. We can put one comma over here. Similarly, 1001 would also have one comma. Cool. If you think of a bigger number like this is 1 lakh, so this will also only have one comma. But if you exceed this by 1, so let's say this is 10 lakhs, 1 2 3 4. Okay, so now this is gonna have 2 commas, right? So essentially what you can do over here is you can just iterate on the numbers from 1 to n, or what I did here is I iterated from 1000 to n, right? Because lower than 1000 will not have any commas, right? So we can iterate from 1000 to n and just calculate how many commas does that particular number contain, right? So for example, I could iterate over this number and I could like this number contains one comma. How can we know that? We can iterate on this digit. Let's say we are on this digit. Now we have seen one digit. Now we move over here. We have seen two digits. Now we move over here. Now we have seen 3 digits. So as soon as we move over here, alright, so we just need to count the number of zeros for any particular element, since the range in this particular problem is very small. So we can iterate for every element which is greater than 1000. So we can start from 1000 itself, because lesser than 1000 will not have any commas, right? So we'll start from 1000, we'll go all the way up to n, and then for each I we'll check that how many zeros it can have. We can place zeros after we have used 3 digits. So we have used 3 digits and then we place a comma here. We have placed 3 digits and we have placed a comma here. Similarly, we can do this for all the numbers, and that's what I have written here. I begin from n, and I begin from 1000 and go all the way up to n. I just increment by count by the number of commas that particular element will have. So I can iterate over all the digits of it. I can keep incrementing. The zeros is actually the digits, so you can replace this by digits, and just a minute, digits, cool, and digits. Okay, so now as soon as my digits become 3, that indicates that I can place a comma over here. So I increment my count by 1. The count essentially indicates the commas, total commas that we can place, and then we reset the digits count by 0, and we keep dividing the number by 10 so that we can iterate over all the digits, and we do this till the end does not become 0, right? I hope you got it. This was just a simple problem, and now let's move on to the second one. Now the second problem, according to the second problem, the constraints are high. The problem is same, the constraints are high. So we cannot directly iterate over all the elements from 1 to n, right? Because n is up to 115. So this will definitely result into TLE. So we basically need to think of something optimal. So if you'll see carefully, you'll observe that from 1000 all the way up to 9999, these elements would contain the same number of commas. Similarly, from 10,000 all the way up to 99,999, these values will also contribute the same number of commas, because essentially I'm not increasing the digits size, right? Either in 1000 or 1001 or 2000, 3000, whatever the digit is, all the way up to 9999, we can only place a single comma over all this, over this particular range, right? So essentially we can get the total number of elements in this range. So that is 9999 minus 1000 plus 1. These are the total number of elements, and the number of commas that it can place is 1. So we can increment my count, the total number of commas that I can place by this particular count. And now I can check for another range, that is from 10,000 to 99,999. What is the let's say this is L and this is R. So total number of elements are R minus L plus 1 into how many commas can I place over here. So that is I can only place 1 comma, so that is multiplied by 1, and then we can do this for all the ranges. And in the end we'll just check, ki my R is, if my L is some power of 10, right? So this is, let's say, this thing. So R would be into 10 minus 1, L into 10 minus 1, right? So this is 99999. So in case my N was something like 7, 2, 3, 4, 5, something like this. So we don't want to exceed the total number, so we'll take the minimum of N and this particular R, right? So that is what I have done. I'm iterating over the ranges from 1000 all the way up to N. My L is the starting point of this particular range, and my R is into 10 minus 1, L into 10 minus 1, which I am doing over here. So L into 10 minus 1, and taken minimum with N. In case we exceed the total number of, or in case we exceed N, I take minimum, I calculate the total number of elements, and this f of I gives the total number of digits that it could have. So essentially you can write the same function to calculate the digits, but I used something else. This was purely done, I saw that whatever we get after dividing by 3, let's say we have this thing, and the total digits is 6, cool. So 6 divided by 3 is 2. That means we can place a comma, 2 commas over here, but since this is a complete power of 3, this is divisible by 3, the total number of digits will decrement this by 1. If we had 7 digits, let's say this thing, 1, 2, 3, 4, 5, okay, this is 7 digits, so we can place 2 commas over it, because 7 by 3 is 2, and 7 is not divisible by 3 completely. So that is why we can place 2 commas over here. Here there were 6 digits which was divisible by 3, so we can only place 1 comma here. So you can divide by 3, and then you can just check if the total number of digits is divisible by 3 or not. This is also one method you can do. Otherwise you can just do the similar thing that you did in the previous problem to calculate total number of digits, and that's it for this problem. Also you'll have to maintain a long, just in case you exceed the answer, because we're iterating over 10 to the 15 elements, so yeah, it could result into an overflow. So yeah, let's move on to the third problem. So the third problem says you're given an integer array nums. A subarray is arithmetic if the difference between consecutive elements in the subarray is constant. You can replace at most one element in nums with an integer. Then you can select any arithmetic subarray from nums. Return the integer denoting maximum length of the arithmetic subarray you can select. Okay. So let's say I've been given this array 5, 7, 9, 11. So the difference between these elements is 1. These elements is 1, and these elements is 2, 2, 2, and 2. So the problem is saying what is the maximum subarray that has the same, or the difference is same in that subarray for all the adjacent elements. So let's say if I was taking difference of the ahead element and the current element. So let's say I plus 1 and I minus 1, or I plus 1 minus ai. Then this difference needs to be constant for all the all the consecutive or adjacent elements in the subarray. So if I choose to take this particular subarray, then the difference of this thing, this is 2 minus 1, needs to be equals to 3 minus 2, needs to be in case we were taking this subarray, so needs to be equals to 5 minus 3. But since 5 minus 3 is 2, which is not equals to 1, so we cannot take this thing, and so I can only take this part. Similarly, I can also take this subarray, because the difference over here is 7 minus 5, which is 2, 9 minus 7, which is 2, and 11 minus 9, which is 2 again. So we can take this subarray, and we need to return the maximum length of the subarray that we can that is a valid subarray. Also, there is one catch in the problem that we can change at most one element. So we can we can pick any element and we need to change it. Cool. Okay. Also, we can choose not to replace any element. So yeah, that is also there. So okay. So I need you guys to think, let's say, can our answer be smaller than 2? If you'll think, then you'll realize that our answer can never be smaller than 2, right? Because I can choose any 2 elements, and since we only have 2 elements, the difference will be constant, right? Problem only arises when we have a subarray of length greater than 2, right? So to think about this problem, we'll need to think about it in in terms of some DP thing. Let's say I'm writing a subarray as 5, 7, 8 and 9, and then maybe I have like 13 over here, and then I have what can I place here, 9, not 13. Alright, I can place a 13 and then 14. Okay, let's just do one thing. 5, 7, 9, 11, and this is like 15, this is 13, this is 15 again, something like this is our array, right? So the optimal answer for this array would be, we can take this 9, 11, okay, let's do one thing, that just a minute, I'm sorry, let's make this 15 and make this 17. Cool. Okay, so now we can choose this 15 and replace this by 13, and now you can see that we can take this complete subarray. We are allowed to change one particular element, right? We can change any one element. So we choose this 15 and replace this by 13. Now you'll see that difference between every 2 consecutive element is 2. 7 minus 5, 9 minus 7, 11 minus 9, 13 minus 11, 15 minus 13, 17 minus 15. The difference is constant over all the subarray, and so we maximize our answer by doing this. So if we think about it in terms of DP, so let's say I have a subarray that satisfies that have a same difference, a left subarray that has the same difference, and a right subarray that has the same difference, and I choose to apply the operation on the current element, right? I choose to apply the operation on the current element, then what exactly this number could become, right? So we have 3 possibilities. Either we could extend this right subarray, or we could extend this left subarray, or we can take and merge both of these together. Let's look at them one by one. So if I choose to extend the left subarray, let's say if I had 5, 7, 9, 11 and maybe 68 or 70, something like this, cool, and I had a number like let's say 15 over here. So what is the best choice for me to do over here to maximize the valid subarray's length? I can choose this 15 and replace this by 13, right? Because if we do that, we can take this subarray, and that is the maximum possible, right? So this was the length of the left subarray that was a valid subarray, because all the differences between the adjacent elements were constant, and so we just changed this particular element, and then we extended this particular range. this particular left subarray by 1. Similarly, if we reverse this thing, let's say 11, 9, 7, 5 and 15, 68, 70, something like this. So we can choose this particular element and replace this by 3, I guess. We can replace this by 3, and now if you take this particular subarray, that is the maximum possible, and all the differences between all the adjacent positions is constant over here. So that is what I'm saying. We have 3 possibilities at each particular index. Let's say I'm iterating on all the elements, and I'm in each iteration I'm saying ki what happens if I choose to replace this particular element. So let's say I'm iterating on all the elements, and by iterating I come over this place, and now I think about what are the 3 possible ways we can perform our operation. So first is we extend the left subarray. So we can always do that. We can always extend the left subarray. Let's say this had a length of 4, so we can increment this by 1. So we can take left length plus 1. Over here we can take right length plus 1. So we can always do these things. We can always do these regardless of anything, right? Whatever the length was for this particular suffix array, for the writer valid suffix array also. So it needs to be valid. Like if it was 5, 7, 9, and let's say 70, 80, something like this. So only this thing is valid now, right? So now I can take 3 plus 1 if I'm talking about suffix. So I can take left plus 1, and I can take right plus 1. These I can always do. And I also have one particular case of this one where I can merge both the right and both the right and the left one, right? So I can choose to replace this particular element by such an element that merges both this thing and this thing. So in that case our answer would be left plus right plus 1, right? So now we need to figure out, okay, so I hope you guys agree with this thing that we can always do these operations, the left plus 1 and right plus 1, because no matter what we had over here, let's say our suffix was something like this, 5, 7, 9, then 13, 14, something like this, and our element was over 1, and then I choose to replace this by 3, and this would be a valid array. Or if our array was 1, 3, 5, and this was 60, something like this, we can choose to replace this by -1, and the array would be valid again. So we can take this array. So the right and the left would always be valid. Now we just need to talk about the merging one, when we want to merge both the left and both the right one. So I need to change this element to such an element that merges these particular ranges. So in order to merge these particular ranges, let's look at this mathematically. So let's say this was I minus 1, this was I, and this was I plus 1. So D is my difference over here, okay? So now I'm saying A of I minus A of I minus 1 is my difference. So A of I minus A of I minus 1, and then A of I plus 1 minus A of I is equals to D. A of I plus 1, and yeah. So the differences of both of these things needs to be constant, right? Because we are merging both the left and the right part. So both the differences of these particular things, the A of I minus A of I minus 1, this thing, and A of I plus 1 minus A of I needs to be same. So now when I add these particular equations, this and this will get cancelled, and now we'll have A plus I plus 1 minus A of I minus 1 is equals to 2D, or the difference would be equals to A of I plus 1 minus A of I minus 1 by 2 is equals to difference. This is my difference, okay? So here 15 minus 11 is 4, 15 minus 11 by 2, so my difference would be 2 here. So this is the difference is valid. So I can choose what was the maximum possible length, valid length of a subarray ending at I minus 1, and what is the maximum possible valid array's length starting from I plus 1, that is suffix 1. I can add both of them, and I can add a +1 over here, because this I can change this element to 13, that is difference of 2, that is I can add 2 over here or I can subtract 2 over here. But if we had something like 11 and 15, or not 15, 16, and let's say we had 14 over here, so differences are not same. Let's say we had some gibberish over here, some gibberish over here. Cool. Now you can see that when you do a of, let's say this was my I, so when you do a of I plus 1 minus a of I, this is actually 5, right, which is odd. And now I'm saying that if it is odd, then we cannot we cannot merge this thing, we cannot perform the third type of operation, because no matter what you try to place over here, the difference will never be constant, right? The difference will of this thing, a of I minus a of I minus 1 and a of I plus 1 minus a of I will never be same if this is odd. You can try to do this yourself, but in the odd thing there doesn't exist a midpoint, right? An integer midpoint. There is no integer midpoint for 5, right? That is why for the odd differences we don't have any option that will not do anything. But if it is even, if it was 6, so 17, so we can place 14 over here. So 14 was good enough, and the differences remain constant. So 14 minus 11 is 3 and 17 minus 14 is 3 again. So we can do this, we can take the left and the right part and merge it. Okay, so that is all for this problem. And to find the maximum possible prefix and suffix subarray, we can just do this. We can initialize the prefix and suffix by 2, because the 2 is always valid. We can always perform we can always construct an subarray of length 2. And now my answer would be, I'm just doing this in a dynamic programming way. If let's say my prefix was 2 and 2 over here, now I'm starting from this particular element, and the difference of if the difference of this thing and this thing is same, that is if this was I minus 1 and I minus 2. So if the difference of a of I minus a of I minus 1 is equals to difference of a of I minus 1 minus a of I minus 2, that is the difference of this thing is the same as the difference of this thing, then we can take whatever was our answer till this point and we can add 1 over here. So this will become 3. That indicates that we can take a 3 length subarray, because 3 length subarray is maximum valid over here. Similarly, when I move on to this 7, now I check that difference of this thing is the same as difference of this thing, which is same again. So I'm saying ki whatever is the maximum possible size till here, take that and add 1 to it to encounter this particular case. So we'll add 1 to it, and now it becomes 4. So that is how exactly, if it was not valid, let's say we had a 15, so we'll just do a 2 over here, because we can always take 2 length or subarray. And now the difference between, let's say, this and this is 8, and 23 is valid again, so this would be 3, because we can take this particular subarray. So similarly, just take a minute to digest this, and similarly for suffix we can also do similarly for the suffix one. So now we'll have the maximum possible length valid array that I can form till the left part and till the right part, right? So we'll have these values, prefix of I minus 1 and suffix of I plus 1. We can just just add them, that is prefix of I minus 1 plus suffix of I plus 1 plus 1 to add this particular element. Otherwise, if we are extending the left thing, so if we are extending the left subarray, this would be prefix of I minus 1 plus 1. If we are extending the right subarray, this would be suffix of I plus 1 plus 1. And that is it for this problem. We can take the maximum of all such cases. So right here I am constructing my prefix and suffix arrays. Note that we initialize this by 2, because 2 length subarray is always possible. Now I just check, I start from 2, I just check if the difference of the current element is the same as the previous element. So we'll take the previous element, whatever was possible till the previous element, and add 1 to that. And similarly we'll do this for the suffix one also. Now I've handled the base cases over here. When I choose to change the first element or the last element, so if let's say my array was this thing, So I can also choose this particular element and choose to replace this, and then whatever was the answer for this particular case, suffix of I plus 1, we can add suffix 1 to suffix of I plus 1. Similarly, if I choose to change this particular element, I can take the prefix of I prefix of this thing n minus 2 and add 1 to that. So these are my base cases. So this is the I've initialized my maximum with these base cases, and now I start from 1 to n minus 1. I first of all I do this thing, I extend the left subarray, and then similarly I extend the right subarray over here, and then the last possibility is to merge both the left and right subarray respectively. So we just calculate the difference of the ahead element and the previous element. If this is divisible by 2, that is, it can be, there exists a midpoint to it, so then only we merge the left and the right part, and now we divide this this by the difference, and now we just check, because if we were performing an operation over on this particular index, then we cannot check this thing that we just did. Where did we do it? Okay, never mind. That I minus a of I minus a of I minus 1 is equals to a of I minus 1 minus a of I minus 2. We cannot do this for I equals to 1 and I equals to n minus 2, right? We cannot do this for this particular index. So that is why I'm checking if I is greater than equals to 2. If I is greater than equals to 2, then I can check for the current element minus previous element, and the previous element minus the previous element to that. If the difference is same, if the difference is the same as what we got over here, then I initialize my left with the earlier prefix, and similarly I check the right one. If the difference is same as that as what we obtained, we initialize my r with the suffix maximum suffix, and then we just add both of them together and add plus 1 to include the current element to it, and then we just return the maximum by taking maximum of all such cases, and that is the answer. Alright, I hope you got it. Now on to the fourth problem, and fourth problem is actually easier than the third one. So in the fourth problem, we have been given coordinates. Basically we have been given this 2D Cartesian plane of xy coordinates. So this is my Cartesian plane, and we have been given these coordinates, right? And then it says that if a point is activated, then all points that have same x or same y coordinate becomes activated as well. So let's say if my point that activated was 1 3, let's say this was 1 3, then all the coordinates that share the same x and same y becomes activated as well. So if this was 2 3, this becomes activated again. Also this was 3 3, this also becomes activated. This was let's say 0 3 also becomes, this was what, or this was 1 0, this also becomes activated. This is 1 1, this also becomes activated, and so this is what, this 2 4 also becomes activated, because this is activated, and this share the same x coordinate. So ultimately these all coordinates becomes activated. So we just need to find okay, so we can add one additional point at any integer coordinate, and we need to find the maximum numbers of points that can be activated. So let's say I had a point over here, this was 5 5. So, and these all points are connected together, these all points were connected with each other, right? And there was one other point 5 5. In order to connect these and these, we can add, the problem is saying we can add another integer coordinate. So we can, let's say, take this thing, maybe 5, this is 5 3, I guess. Yeah, this is 5 3. We can add this particular coordinate, and now this shares the same y coordinate, so this also becomes activated and this also becomes activated, right? So that is all for this problem, that we need to merge the largest possible graph, I think. So we can create this particular graph in easier words. We can take all of these coordinates and group them together. We'll just see in a bit how can we group them together. And maybe if there were some other coordinates, let's say this was 6 and 5. This is not 6 and 5, this is 5 and 6. This was 7 and 6. This was 8, maybe 8 and 6, and 9 and 6. 8 and 7. Cool. So these coordinates are also, will activate each other. So this is just a one graph. This is, you can say that this is one graph, and then this is one graph, and we can merge this graph with each other by adding this particular coordinate which shares the same row or same column, right? We can merge both of them together, and then that is my answer. So essentially all we need to do is group all the points that we have together, all the points that we possibly can, all the points that either share the same x coordinate or either share the same y coordinate. We can group them together, and we can create all these groups, and then we can just take the maximum two such groups. So maybe there was another group of, let's say, 10 and 10 and 10 and 11, but we choose to ignore this because these are the maximum two groups which has maximum number of coordinates, right? So it will make sense for me to merge these two groups together, not this two, right, or these two. This will not make sense. We can choose two biggest groups and we can merge them together, and that is my answer. So what comes to your mind when you hear this group thing? I did this with the disjoint set union, DSU, to group all the similar elements together, and we just find the maximum element, maximum group, and take the two maximum groups and add one to that answer. So size of this group and size of this group, and then we add one integer coordinate to group both of them together. So that is my answer. So that is what I do. I initialize a disjoint set union. I have a parent and size. This is just a standard implementation of DSU, just the direct implementation of DSU. I didn't change a single line over here. And now I created DSU. I create two maps, one for x coordinate and one for y coordinate. This will indicate that I have seen this x coordinate before and I have seen this y coordinate before. So now I see that I've searched in my map if I've seen this particular x coordinate before. If I've seen this x coordinate before, then I take the union of this coordinate and whatever was the index of the particular coordinate, right? The one that I've already seen. If I haven't seen that particular x coordinate, then I add my current index to this particular x coordinate, right? Similarly, I do this for y coordinate as well. And at the end, we'll just obtain the largest two groups by size. So we'll just check. We're just iterating over all the nodes, and then we're checking if the parent of I equals to I. That means if it is the ultimate parent or the head or the root node of the particular graph. So this you need to have an idea of how DSUs are implemented in order to solve this problem, I guess, directly with DSU. Otherwise, I think you can there exists a way to solve this by graphs as well. So this thing is called a root node. So that is what I'm checking. If my parent of I equals to I, that means it is the root node. So then I push the size of this particular group to this array. Then I sort this in descending order. And if the size is greater than 1, then I can take just the maximum two elements and add one to that. Otherwise, if the size is 1, I can take the only group and add one to that particular group. And that is all for this problem. This was just the direct implementation of DSU. If you know how to implement DSU, you can do this directly. Otherwise, if you want to understand this implementation, I'll recommend you to study DSU first. And then this problem is just a piece of cake, because we are just constructing the group, the similar elements that share either x or either y. We're grouping them together by maintaining two maps of x and y coordinates respectively. And that's it for this problem. I hope you got the implementation, and I hope you liked the problems, enjoyed the problems. and I hope I was able to explain to you these concepts. And if you are watching, then thank you so much. I'll see you guys in the next one.